So you can think of a function like a machine. So x is what you input into a function. It could be a number, could be a variable or a combination. And the output is basically y, but we don't call it y anymore. So in other words, like when you think order pair like x and y, think of the x value is what you're putting into a function. The y value is the output of the function. But our new name for y is actually just called f of x. So f of x is the output of the function. So well, if the function is called f, in this case it is. If it was called g, it would be g of x, right? So that's the idea. So this is what some function might actually look like. So this is again, like a machine. So we're going to plug in a number into this one. So let's do f of 3. So everywhere there is a 3. So all this is, think of this as just substitution or just plugging in. So what we're doing is everywhere there was an x, we're going to plug in 3. So this will be f of 3 equals 9 minus 2, which is 7. So the output, when I plug in 3, f of 3, but notice this is not the same thing as f times 3. That's a totally different. F is not a variable. It's the name of a function. F is the function f. And so f, I'm evaluating f at 3. But typically we just say f of 3 equals 7. That actually means the ordered pair 3, 7. Input is 3. The output is 7. So a machine has an input and an output. Be careful, because when you plug in a negative number like this, f of negative 2, same function. So let's plug it into that one. So instead of x squared minus 2, I'm going to plug in negative 2. Now notice where I have the parentheses there, because that's where students will get this wrong if you don't use parentheses correctly. So the x is being squared, which negative 2 is x, so it's being squared, which means that's a positive 4 minus 2, which is 2. So f of negative 2, the answer is 2. Now you can also, what is the domain and range of that function? So the range is hard to find in this case. Well, we'll kind of look at it. So the domain is all reals. So the domain are the x values there. I guess we'll get more into this in just a minute. But I can plug any value in for x and get a real answer in reply. So we just say all reals. Domain can be anything. There's no restrictions. A lot of functions have domain as all reals. The range, we could at least kind of think about in this problem. Some problems are starting to think about. This one's not too bad. I have to say this number can't be negative. Do y'all agree with that? Like even if you have a negative number, when you square it, it becomes positive. So the smallest that could be would be 0, if that makes sense. So 0 minus 2, I think the range would go y is greater than or equal to negative 2. The smallest it could be would be if that x value was 0, it would mean the y value or the f of x values would be negative 2. So it would be negative 2 or higher. If you actually look at the graph, and again, we're not quite ready to graph all this yet, but the graph of this looks kind of like this, roughly. The lowest point it hits right down there is at 0, negative 2. So the range really is more easily gotten from the graph of a function. And so the lowest it goes, the minimum value is negative 2 there. And it goes a lot higher, it goes up to infinity, so y is greater than or equal to negative 2. You can also plug numbers in there. So what I mean by that is, I think the function here was f of x equals x squared minus 2. What I mean is you can plug in variables. Okay, so if the question was, and they could definitely ask this, what is f of 3x? So everywhere there's an x, I'm going to plug in 3x, right? So this is going to make, so this is going to be 3x squared, which is 3x times 3x, which is 9x squared minus 2. So my answer to f of 3x, which is the name of what we plugged in 3x into the f function, is 9x squared minus 2. Notice the answer has an x in there. When you're plugging x in, it makes sense your answer is going to have an x in there. Okay, this is the old school way of asking questions in math class. Remember just a few days ago, we might ask if y equals 2x minus 6, solve when x equals 3. Of course, you just plug it in. The new cool way of doing this is to use function notation. Same function, but instead of y, we're plugging in f of x. And instead of saying this big long sentence, solve for y when x equals 3, that's a lot of writing for a math teacher. This is a lot less writing. What is f of 3? Well, we can do f of 3 pretty quickly. So this will be 2 times x minus 6. Again, we're plugging in 3 everywhere there's an x. So right there, we're plugging in a 3. So we get 6 minus 6, which is 0. So f of 3 is equal to 0. So you can plug in, it's just a faster way of notating what to plug in where, basically. Okay, here's the formal definition of, I definitely want you to write this down, of domain. Domain of function is, sometimes I should say all the x values or all possible x values, but this is the domain of function is a set of all possible x values that will make the function output real y values. So I don't know why I made that too big there. So you want the y values to be real y values there. So not imaginary, not undefined, stuff like that. So let's just graph this in our Inspire to see what it looks like. So I'm going to graph this. So let's go. And notice the Inspire does function notation. I'm on F3, you might be on F1 or F2 or something. You get control divide for the fraction template, 1 over x minus 2. Okay. It looks kind of weird. Like this is the graph of that function. Look at the table. I wonder, let's look at the table. So you can see the table hitting Control T. It's kind of neat. And you may notice like it's got a lot of different x values I can plug in, but when I plug in 2, it says undef, which means undefined. I'm going to hit Control T. So when I plug in 2, there is a problem. Let's just look back at the thing. Why is there a problem when I plug in 2? So let's do it. Let's do f of 2, right? We just learned how to do function notation. If I plug in, so if I do f of 2, I get 1 over 2 minus 2, which is 1 over 0. What is 1 divided by 0? So if you do that in your calculator, so control divide 1 divided by 0, it is undefined. There's no way to even divide by 0. We can't do it. So that's not really a number. It's undefined. Notice we said if the output isn't real, it's not part of the domain. So x can really be anything. Here's what I mean by that. So like if I were to go back to the graph here, if I hit the trace key, menu 5, 1, I can mouse to the left. X has all those, you see those points displayed at the bottom of the screen right down there? Got lots of different points. But if I plug in 2, so if I plug in 1, it jumps to that point. If I type 2 and press enter in trace mode, it'll jump there and it says the value is undefined. Again, and that's really the only place that this function is undefined. If I go to the right here, just a little bit more to the right, you'll see that, I could graph the rest of the graph. It's a point of discontinuity in the graph. I have to pick up my pencil to keep moving from that point. So it is not part of the domain. So the domain of this function would be all reals, except x cannot equal 2. So that's how we write the domain. You could write it in interval notation, if that makes sense. It would be 2 intervals. I guess it would be from negative infinity to 2, not including 2, union with from 2 to infinity. So if you prefer writing it that way, I think most students write it this way. If you prefer writing it in interval notation, it's 2 different intervals. They're separated by an open circle or kind of like an undefined point there, an undefined value there at 2. So let's try, let's see if there's any more examples. Oh, there is. Okay, so let's try square root now. So this one also causes some issues, and I know we've talked about imaginary numbers, I believe, and so you can't, if you take the square root of a negative number, it's not going to work out well it's going to be imaginary, right? Which is not real. Again, to be part of the domain, you have to get a real output, a real number output. And so you might be able to think that through in your head, like if that value was like -5 or -6, that's going to be a negative number here. It's going to be imaginary result. It's not going to be part of the domain. So what I always do for this kind of problem is I take the radicand, whatever's underneath the radical, x plus 4 in this case, right? So I'm going to pull that out. And I say that value must be, it can't be negative. So with the inequality, to say that, you say that must be greater than or equal to 0. So that quantity inside of there, because I don't want that to be negative, if it's negative, it's not real for the output. So you say it must be greater than or equal to 0, and just solve it. Subtract 4. Subtract 4. I write my 4s like that. I don't know why I write that like that. So x greater than or equal to -4. So my domain is actually just that. One thing that's nice if you do it this way, it automatically comes out in the form you want. That's the domain. You could also write it with interval notation from -4 to infinity. That would be as well. Okay, as well. So the two things you got to know: the denominator can't be 0, and values under a square root can't be negative. So it actually could be 0 or positive. So we must say it's greater than or equal to 0. So you usually set it greater than or equal to 0. So this is about the toughest domain problem we can have because it's got two things going on. Let's look at the denominator first. What value can x not be in the denominator? Again, the denominator can't be 0. And so if you're struggling with that, you can say x minus 1 equals 0. So add 1 to both sides, x equals 1. So the domain of this guy would be all reals, except x cannot equal 1. Now let's talk about the numerator. For the numerator, we take whatever's inside of there, in this case, 3 minus x. We're going to pull that out, and we're going to set that greater than or equal to 0. Greater than or equal to 0. So I'm going to solve. I'm going to subtract 3, so I get negative x greater than or equal to -3. Divide by -1. Don't forget to switch the direction of the sign. You get x less than or equal to 3. So I have two domains. I have that domain, and I have this domain. So to be part of that fraction or part of that function, I need both the numerator and the denominator to match. So basically it's kind of like an and sign in between these two. So if you look at the number line, like if this is 1, if this is 3, the red graph will be less or equal to 3, so closed circle, arrow that way. The blue graph will be everything's aligned. Oh wait, let me switch that. Everything's aligned except there's like a little open circle at 1. Where it can't be. It can't be equal to 1. So where is the overlap in this graph? Where do these two graphs overlap? They tend to overlap like here. Oh wait, not that far. They overlap here and then here. Right, so that's really two different intervals. You could say with interval notation this way, negative infinity to 1, not including 1, union with from 1 to 3, bracket at 3. I think that's probably the best way to write it there. It's just as two separate intervals when you do that. I guess you could write it from, so x, you write this as x is sandwiched in between 3 and 1, or x is less than or equal to, or sorry, less than, do that again, x is, or x is less than 1. So why did I put it like that? I wrote that really funny. So x is in between 1 and 3, sandwiched in between, or x is less than 1. It's a lot tougher. It's tough to write it. It takes a bit of thinking to kind of think backwards and think about each interval there. But it's two separate intervals would be our solution. That's a very difficult problem, I would say. This one, even though it cancels, like this actually, so this would be x times x minus 2 over x minus 2. Even though this cancels, the domain is all reals, but x still can't be equal to 2 because the original problem before it canceled had an x minus 2 in the denominator. So you cannot substitute 2 into that function. Okay, so we're going to learn how to do a piecewise function. So we'll get more into this tomorrow. So if you don't get this fully today, that's okay. I just want to do one example of a function that's broken up into different pieces. You can kind of see that in this case, it's got this f of x is really made up of two functions. The bottom one looks linear. So it looks like mx plus b kind of linear. So I'm going to graph that line. Looks like it has a y-intercept of -3. A slope of, there's an understood 1 there, so a slope of 1 over, up 1 over 1. This graph looks roughly like this. Let's make a bunch of slope points first, so I'll try to graph that and connect all the slope points. Looks like that. Now, a couple things about that line. One is, I probably should have looked first. It looks like the sign there is x is, so x is greater than, let's talk about this over here for a second so you understand. This part is the domain. So the left-hand side there, the linear line, is the function. The right-hand side is the domain that I want that function to be graphed on. So I don't want to graph the whole function. I graph the whole function, by the way. Fortunately, I have an eraser. I can erase some of it. It says I only want my domain to be bigger than 1, my x value. So like, for example, if you kind of look at this point right here is the point 1, comma, -2. So that point is where x is equal to 1. I want x when it is larger than 1, but I don't want it when it's smaller. So all of this part of the graph, when it's smaller than 1, I don't want. And really, to be technical about it, I actually want it larger than 1, not equal to 1. So I have a closed circle there, but actually, it most definitely should be an open circle right there. So because it does not include 1, it's not equal to 1, it's larger than 1. So any point on this blue line now fits the domain right there of x greater than 1. So I had to graph the whole line and then erase the part that I did not need. I'll just try this next one. So again, remember this is the same thing as y equals, right? So this function right here is y equals x squared. So you might not know that function by heart right now. We'll talk about tomorrow, like how you should memorize certain kind of functions and stuff. So let's just plug in a few points. So let's plug in a few x, y points. Instead of calling it y, I'm going to call them f of x, but you could call them y. That's the old way. The new way is f of x. So I'm going to plug in like just a couple of x values, like a few positive ones and a few negative ones. This should give us a good sense of what's happening in the graph. So if I plug in 0, 0 squared is 0, so that's the point 0, 0. If I plug in 1, 1 squared is 1, that's the point 1, 1. 2 squared is 4, so 2, 4 is a point right up there. Be careful here, plug in with parentheses, so I'm squaring a -1. -1 times -1 is positive 1. I'm also squaring a -2, which again becomes positive, that's going to be 4. So -1, 1, and -2, 4. And this kind of looks like, remember we've talked about this shape, we've seen it before, it's a parabola. Well, for some reason I went a little spastic there, but looks something like that, roughly. That's a pretty good graph. Okay, but I have to erase part of this, right? Because the domain we want that function when it's less than or equal to 1. Well, here's where x is equal to 1. So this is the point 1, comma 1. I don't want anything greater than. So this right-hand side of the graph is gone. And at 1, it is actually less than or equal to. So I do want a closed circle there at 1. So I'm actually happy with that graph. That is what this function looks like. It's a piecewise function. They don't necessarily connect. Sometimes a piecewise function, the pieces will connect. In this case, there's a point of discontinuity. But the range, interestingly, I mean, the domain is all reals. The range, it looks like the lowest point is at -2 there. So probably y is greater than or equal to -2, kind of like that graph we had for the absolute value or that other parabola we had. Okay, that's enough for today. So just kind of introduce you to the flavor of what a piecewise function is.